All right, when you need to get a fair snapshot of a big group, what's the first thing that pops into your head? Probably something like, just pick people at random, right? But here's a thought. What if being purely random isn't always the smartest play? What if, sometimes, it's not even the fairest? Let's dive into why.
So, we're going to kick things off with a scenario. On the surface, it seems totally fair. But as you're about to see, it really pulls back the curtain on a huge weakness in just leaving everything up to pure chance.
And this is really the heart of the matter, isn't it? We take a sample because we want a tiny, perfect mirror of the whole population. But does random luck actually promise us that? You might be surprised to hear that the answer is a big fat no.
Just take a look at this. Imagine you've got a population that's mostly men, but has a small, important group of women. If you just close your eyes and randomly pick a sample, it's totally possible, just by the luck of the draw, that you'd miss the women completely. You'd end up with a sample that looks nothing like the real world.
And here's the crucial part. If men and women feel differently about whatever it is you're studying, a sample like that isn't just unlucky, it's just plain wrong. Your results would be totally misleading.
Okay, so if pure chance can lead us astray, what do we do? How can we be random, but also make sure we get that balanced picture we need? Well, luckily, there's a much smarter way to do this.
The solution is this fantastic technique called stratified sampling. And honestly, the logic behind it is just brilliant. Instead of fishing from one giant pond, you first split that pond into smaller, important little pools. We call these strata. Then you go fishing in each and every one of them.
It's a really clean three-step dance. First, you split your population into those meaningful groups. Think men and women, or maybe different age ranges. Second, you take a random sample from inside each of those groups. And finally, you stitch those little mini samples together to create one super sample that you know is representative.
You know, the Lego analogy is just perfect for this. A simple random sample is like plunging your hand into a giant bin and just hoping you get the colors you need. Stratified sampling is way more deliberate. It's like saying, okay, I'm going to make sure I grab some red bricks, some blue bricks, and some yellow bricks. That way, you know your final model has all the right parts.
Okay, theory's great, but let's see this thing in action. We're going to look at a real-world case where the differences between the groups, the colors of our Legos, are absolutely massive.
See, when you look at farms in the United States, they're not all the same size, not even close. You've got these huge regional differences, and that creates a massive headache if you're trying to figure out the national average by just randomly picking farms.
And this chart right here just lays the problem bare. Check out the box for the West, marked with a W. It is wildly different from the others. The average farm is way bigger, and the sizes are all over the place. Now, if you sampled randomly, you could accidentally get way too many of these giant Western farms, or not enough, and your whole national average would be completely thrown off.
Once you see the problem laid out like this, the solution is just staring you in the face. You treat each region, Northeast, South, West, etc., as its own separate group, its own stratum. That way, you guarantee that the unique nature of each region is properly represented.
And here's exactly how they did it. So smart. They wanted a sample of 300 counties total, but instead of picking 300 from the whole country, they took about 10% from the Northeast, 10% from the North Central, and so on. It guarantees the final mix of counties looks just like the real geographic mix of the country. Beautiful.
So, all that extra work, splitting things up, sampling from each group, was it actually worth it? Did it make a real difference? Let's look at the payoff.
This table tells you everything you need to know. That column on the right, standard error, just think of it as a fuzziness score. The lower the number, the sharper and more precise your measurement is. And look at that. With the exact same sample size of 300, the stratified method gives us a much lower fuzziness score.
So what does that really mean? It means our estimate of the average farm size is way more reliable. We've shrunk the margin of error. It's really the difference between looking at a blurry, out-of-focus photograph and a sharp, crystal-clear one. And we can actually put a number on that improvement. By being smart and stratifying by region, the researchers cut down the wobble in their estimate, the statistical variance, by a massive 25%. That is a huge win in precision.
But here's the real kicker. If you wanted to get that same level of precision using the old-fashioned random method, you would have had to sample way more counties, which means more time, more money, more resources. So stratified sampling isn't just more accurate, it's also way more efficient.
All right, let's bring it all home. What's the big takeaway here?
Why is this such a critical tool in the toolbox for anyone who works with data?
Look, it really comes down to this. Stratified sampling is like insurance for your data. It protects you from the wacky results that pure chance can sometimes give you. It absolutely guarantees that those important subgroups are included, and, like we just saw, it can save you a ton of time and money. It's just a smarter way to work.
So I'll leave you with this. The next time you see a poll or a study pop up on the news, take a second and think. Did they just roll the dice and hope for the best? Or did they sample smart? Did they use a clever approach like this to make sure their picture of the world was truly in focus? It's worth asking.